Hi everyone, welcome to my talk on demystifying privacy preserving computation. First and foremost, I would like to thank Build Stuff community for inviting me over here. It's my first time in Lithuania and I am very honored to be here today. And if you feel that my voice is not hitting the chord, it's because after a 14-hour flight from San Francisco, the jet lag is hitting right now. So, it's interesting how time zones work. But the aim of this talk is to share what privacy preserving computation is. It's a very vast field and especially useful today with AI and machine learning. And by no means is this an exhaustive, we'll not cover to a very large degree what the active research right now is, but I would like to give you flavors that you can take with you and then dig into it. So the agenda for the talk is as follows. I'll talk about myself, what I do, and I will talk about why we are talking about this topic. This privacy preserving compute, what exactly does it even mean? And why is it important? And then we will touch upon four major techniques. Some of you may be familiar with a couple of them. Federated machine learning is very common these days with the proliferation of AI and ML. Then there's differential privacy, secure multiparty computation, and homomorphic encryption. And we'll try to tease apart what each of these mean. I also have some code snippets to show you how you can actually try out these techniques for PPC. I'm a software engineer at Netflix. When you watch Netflix, you see shows and movies being recommended to you. My job is to make sure that we train machine learning models on your past history of what you've watched, what you like, and then recommend the appropriate movies. It is not just the fact that a movie is recommended to you or a show is recommended to you. It's also that if you look at a show, even in your account, if there are multiple profiles, the same show will have different images and different snippets shown to each person. This is because we actually train the models to understand what you or your profile likes. If you're someone who likes sunshine, who likes flowers, then we'll try to show that image without revealing the plot of the movie to you. And also we'll try to show you the actors that you've preferred in the past. So this is how intricate the process of machine learning training in Netflix is. As you can tell from my picture, ever since I started working there, I've lost a lot of hair. I'm also co-founder at GoEB1, which tries to use AI and machine learning to help immigrants in the US become thought leaders. I am a TEDx speaker. I talk on blockchain, cloud computing, machine learning, and I have worked at companies like Apple, Samsung, Cadence, and Box in the past. Um, so this entire thing of privacy preserving compute started really when I started digging into blockchain. Now, especially in the last 2 weeks, blockchain has been interesting because people are making money. And after 2 years of not making any money. But why is blockchain special? Uh, Forget about all the noise, marketing noise, and everything that you hear. But really, it boils down to the fact that before the internet came, um, data was always centralized. You can do three things with data. You can send the data, you can store the data, and you can process the data. What the internet did is sending of the data became decentralized because of the internet. But what blockchain promises or is doing is it is actually taking out the storage and inherently the processing of data also out of the centralized waters. That is why blockchain is considered at the infrastructure level a very revolutionary technology. However, by itself, blockchain today still has limitations. And when I started looking into privacy preserving compute, one of the things that was very different that I saw in the blockchain is, and the world has changed today, but really when you are giving someone some coins, you have your wallet address. People can look at your wallet address and look at all the transactions that have happened. So in some ways, yes, there are coins for which they anonymize the wallet address and you cannot really know how many coins were transferred. But to some degree, there is a loss of privacy of information. It is similar to if I give you my email email address, and you can actually peek and look at all the emails that I've sent or received. And that led to the rabbit hole of privacy preserving compute. On the other hand, I'm sure a lot of you may have noticed that when you are in a room talking to people, you suddenly start seeing advertisements based on the conversations that you're having. I don't know if it's true in your case, but it is definitely true in my case, where if I'm talking to someone, hey, you know what, I'm planning a trip somewhere. The next moment I go on Instagram, I start seeing, flight tickets and things there. Um, and this actually is a true story. Like one of my friends said that they were talking to someone on WhatsApp about a credit card. WhatsApp is end-to-end encrypted. And even then, they started getting credit card advertisements on Meta. So this is to say that the data that you are giving out, or the data that you're generating, is not really private. It's also important to call out the distinction between privacy and security. This is similar to authentication and authorization. Security is similar to authentication, and privacy is similar to authorization. And it's important to understand these differences because most of the techniques that I talk about today will delve into privacy alone, not into the security aspect of it. You still need to log in into apps. Still need to have a security layer. But how many permissions a user gets, or how much data are they willing to give to get a utility, that is what we'll try to cover here. There are also data breaches today. And in the next few slides, I'll show you the amount of breaches that have happened in the last year. But this is because, to some degree, we all are putting our data into some databases. Some of these applications have databases, and every now and then that data gets compromised. This makes all of us wonder, why was data sitting there in a form that made it compromisable? Can something be done? Can applications or algorithms of the future look at an encrypted form of our data and not the real data and still be valuable to us? This was what I was talking about. There are data breaches all around us. The Marriott data breach that happened in 2018 actually compromised 500 million records containing personal information of guests. Every 2 years in the United States, there is a data breach for our social security numbers. And we get this, thing that, hey, for the next 2 years, you'll get free social security review or whatever, whatever. Uh, at least in my 15 years in the US, I've had like 5 or 6 breaches like these, which is 143 million in the latest one that were compromised. So this is one end of the spectrum where you've put your data and you're running into breaches. Let's look at the other end of the spectrum. Let's say that you are a machine learning scientist or an AI person. It's better to call yourself an AI person now. And you want to study the impact of COVID-19 on lungs. And this is actually an image of a patient who had COVID-19. So what would you do? The first step is you want to train a machine learning model, and you will download millions of images of lungs. But where do you get them from? You have to buy data sets from hospitals. It's not like MNIST or other data sets that are available. Now, to buy data sets, you need to get funded by a VC. You need to create a business plan. This is to say that some of the most pressing challenges that we face in healthcare today are because we have compliance reasons because of which data cannot be shared. If today there is a hospital that has patients that are having a new kind of disease, that data cannot be shared by other hospitals because it's compromising patient information. So to some degree, what's happening is, on the one end of the spectrum, we're giving out a lot of data to get utility. On the other end of the spectrum, we are not giving out any data, and therefore we are running into problems. So we are not solving the hard problems around us because we are not able to define to what degree do we want privacy of our data. And all of this boils down, at least in this case, because data is private. So the fundamental question we have to ask is, can we answer questions without looking at data? What does that mean for recommendations? If Netflix or Amazon doesn't know what you've watched in the past, how can it recommend what you should watch? And do we have to compromise on utility for privacy? Like in this case, if you don't give out your data, you you inherently either have to pay for the service because your data is effectively paying for it. And privacy preserving compute, which is why this is important. It is a technique that allows you to get utility with privacy and security. So on one end of the spectrum, you have full privacy and no utility, like the hospital case. On the other end of the spectrum, you have full utility and no privacy, like the breaches that I shared. We want to be somewhere in the middle. We want to not give out our data, but we still want to leverage recommendations. We still want to get recommendations. Is it even possible? That's what we'll try to cover today. So in simple terms, you own your data. Your data is not shared in a meaningful manner with applications. The algorithms and all of the compute run on top of your data, but do not necessarily know the exact data. And there are several flavors out there. We will barely scratch the surface here. There's federated learning, differential privacy, and the other two. So let's begin by talking about federated learning. Uh, so federated learning, in simple terms, is it's very simple to explain. Let's say that you have a machine learning model. Today, the model is hosted on a centralized server. You collect data from different places, and that data is shipped to the model to train the model. Later, the same model is used and you ask the model questions, and that is the inference side. But in this case, you're bringing the data to the model. Federated learning flips it. Instead of bringing the data to the model, it takes the model to the data, which means what Apple did in case of Siri. When you talk to Siri, you may think that Siri is responding based on the data that is coming and going, or rather going out of your device to Apple servers. But that is not the case. Apple has shipped some models to your device. So when you talk to Siri, it's actually locally inferencing. Apple doesn't even know what you're talking about at that point. Now, this is the power of federated learning, which effectively means that every phone has its data within it. The data is not sent out of the device at all. It's not just Apple. Google, when you start texting in Google Chat, that is still local to your device. It is not sent to Google servers. So in federated learning, you train your machine learning model in a distributed manner on different devices without collecting data in a centralized repository. And this is very simple to demonstrate. You on the first step is you have a model, you ship it to different devices. These devices could be edge devices, IoT devices. In areas where the network connectivity may be poor, this is a very, very good technique. And today, with machine learning models being quantized or compressed, this is a reality. And then each node will operate on its local data to update some parameters of the model. Once all of the nodes have updated the parameters in step 3, as you can see here, um, these parameters will be shipped back to the centralized location and that will update the model. So we will average it out. So what are the advantages of this? Only the model gets exchanged between devices and the central repository. The data is not exchanged, so inherently this is compliant. If you think about GDPR or other such compliance necessities that are there in different regions of the world, then this can suffice. But there are disadvantages. Devices may not have resources to compute. Uh, some devices have less memory, some devices have more memory. And when you compress machine learning models, you will lose accuracy. So if you have compressed a model down to like 1 bit representation or 1.5 bit representation, which Meta recently had a paper about, then you may not get the accuracy levels, and that is a challenge. Not only that, in this case, you are sending back the parameters to the centralized location. So there is a leaky abstraction where the parameters can still be sniffed. So it's not really private. Um, this is a very good example of how hospital data can be exchanged using federated learning. Because let's say that the example that I shared of a new disease being discovered in one of the hospitals, you can actually have a model shipped to locally to that hospital, trained on patient data in the hospital premise, and the model gets updated, and then you can use another hospital's data to validate whether there is a pandemic or not. Um, there is a paper that talks about the privacy leakage from federated learning. So if you're someone who's very interested into this, I would recommend looking at that paper. Now let's show with code how this is possible. So this is how federated learning can be implemented. In this case, I have used PySift. PySift is a library that is used for federated learning today. And in this case, I have simulated two clients. Each of these clients have some data inside them, as you can see here. And these data sets are created. What I've done is I've defined a simple linear model here. And in this particular on this particular side, I am training the model on each device separately. And finally, once both the devices have the model trained locally, I will average out the model. So what that means is I will send back the parameters to the parent model, and it would be an average of the parameters that have been trained individually. Coming to the next one, which is differential privacy. So far, all good? Okay, good. So differential privacy there's a claim here. So it's a bit complicated, like the way it's worded, but this is the official definition. You will not be affected adversely or otherwise by allowing your data to be used in a study or analysis, no matter what other studies, datasets, or information sources are available. It's a tongue twister. I had no idea what this line meant. So I tried to explain it, I thought of having an example. Let's say I want to know how much money all of us have. What's the average amount of money we all have in our pockets right now? Cash. One simple way is I ask each one of you, tell me how much cash you have, and I average it out. But you're losing your privacy because you're telling me the data. The other way is I tell you to add a random number to it and give it, plus minus $20. So I'll get a lot of data. Now the law of large numbers says that as the sample size grows, the mean gets closer to the average of the whole population, which means effectively your random noise that you've added cancels out. And it is not intuitive. You may think, nah, this is not possible. But I'll show you an example of a simple case where the sample size is very small and you still get very close to the number that you desire. So differential privacy effectively is a framework. It's not a technique by itself. It's not an algorithm. But so far, people were coming up with research in this area of privacy, but they did not have a framework to quantify how much someone is willing to give out their privacy for utility. Differential privacy tried to or attempted to have such a framework in place. What differential privacy's key query is that let's say you have a database of multiple entries of multiple users. If you remove a single entry of a single user from that DB, the query's results will not be impacted significantly. Like in the case of averaging out everyone's salaries or income, if I remove one person's information out of the database, the average will not be affected, which means that the query itself is differentially private. There is inherently nothing that a customer or a user is revealing in this case. This is just a fancy way to show the same thing. If you have a data set of entries and if you remove an entry, but if the sum or the average rather remains almost the same, your privacy is protected. Otherwise, it is compromised. So what does it promise? It promises to protect individuals from any additional harm that they might face due to their data being in the private database X that they would not have faced had their data not been a part of that database. And what does it not promise? It does not guarantee security, in simple words. So this is a privacy technique. It does not guarantee that what one believes to be one's secrets will remain secret. This is an example of a code that tries to show what I mean, which is you have sensitive data. In this case, I've defined some noise. Epsilon, you can think of it in simple terms as the noise that I'm adding. And I have implemented a privacy function which tries to perform, there's a true sum and then there's a noisy sum. The true sum is actually the sum that we get, which is 368. But if we still do with a noisy sum, we are not that far off. It's 363. And these are just like 10 samples, I think, not more than that. So as the sample size grows, this number gets closer and closer. One thing to notice that in this case also, it works fine, but you still have some idea about what the data is. It's not, there is noise added to data, but you still know the ballpark of the data. It is, it's being used actually at a bunch of places. The two well-known applications, one of them is Google Chrome. Actually, Google Chrome uses this approach to discover frequently visited pages in order to improve the caching and the prefetch mechanisms. And iOS uses it to discover words and emojis to improve the language models that is used in typing assistance. Microsoft uses differential privacy to get telemetry data from devices that run their operating system. The US Census Bureau used it in the 2020 census. But this too is fraught with some challenges. So there was a study that said that although Apple claimed to be differentially private or have differential privacy, the amount of noise that should be added to the user's information was not sufficient, which means that somewhere the privacy is still in the gray area. People could understand the ballpark of users' data. That's what this, I'm kind of summarizing all of what they've written here. So yes, it is fraught with some challenges. That is the summary of differential privacy. Now let's talk about the third one. So far good, everybody? Perfect. Secure multi-party computation. The name is again very long, but it's simple. We'll try to understand what this is. So it allows multiple parties to together perform a computation without any of the parties knowing what the other parties have. I'll explain what this means. Let's say we want to know the average salary of people, A, B, and C. And we know that this is the data. What you're doing here is you're simply shredding the data in random parts and distributing the part across all nodes. So A is splitting the data between A, B, and C and giving them some random numbers. B is doing the same and C is doing the same. If you sum all of them, it'll come back to the same total. Now what's happening is B, for example, knows a part of A's data but has no idea what A has. It just knows the share that was shared by A. And let's say we want to compute what's the average salary they all have. Simple way to do it, I mean, you can of course compute it this way, but the other technique is A has all the shares of A, B, and C, sum them all up. Do the same with B, do the same with C. Now you sum all of these up and you get the sum of all that they have, and you can figure out the average. What I have done here is this. B and C have no idea about A's salary, and similarly A has no idea about B and C's salary. But the query is such that even without not knowing the data, by just talking to each other, in this case, they are communicating the sums with each other because you are adding all of these together. You are able to still get to the answer. In simple terms, you have data, you shred the data into pieces, and for all you Harry Potter fans, you Horcrux the data effectively, and you distribute it amongst participants, let them do their individual computation, collect the data, let them talk to each other to compute the sum or whatever they want to do. And then you can reconstruct and get the computation result back. This is what secure multi-party computation is. So the blueprint is you encode the data into a secure distributed format, and you have to shred it and share it. And we'll get into how that is done. You perform computation on the securely encrypted distributed data, and then you reconstruct the encoded results. So it's simple to understand if you look at the steps. Now let's get into the interesting part. So how do you split the data? I used to hate polynomials when I was in 12th grade and I was learning about it because I never quite understood it. And when I was looking into this, the explanation was all about polynomials. So I had to kind of revise whatever I had learned in school. And I'll try to do the same here. Let's say I give you a point and I ask you how many lines pass through this point. Infinite number of lines. And if I give you 2 points, there's only one line that will pass through it. If I give you 3 points, there's only one degree 2 polynomial that will pass through 3 points. And you can extrapolate the same thing. Let's say I have a secret a secret number that I want to share amongst participants. One way to do it is put the secret on the y-axis. In this case, let's say the secret was the number 10. So you took a point on the y-axis with x equal to 0, which is this point here. Make a random polynomial pass through it. Now what you do is pick random points on the polynomial. And these points, share it with the participants or with the nodes. What this does is, unless and until you are not able to get t plus 1 non-malicious nodes giving you their share back, you cannot construct the polynomial, and thereby you cannot get back the secret, which is this. Each participant by itself will have just the share that they've been given, and there can be infinite number of polynomials that pass through it. Why is this important? It is important because there are many studies that claim that in the future, when quantum computing becomes a reality or a commercial reality and viable solution, then all of the algorithms that we have around encryption and all will fail. However, if in this particular case, even if quantum computing were to become commercially viable, whenever it is, this will still hold its ground. And this is called information theoretically secure, or ITS secure algorithm, which means that there will be infinite possibilities and it's very hard to say which possibility is true in that case. So this method of secret sharing is the Shamir secret sharing algorithm. And information will be broken into many shares, but you only need, out of the n nodes with which you share the information, you need t plus 1 nodes to be non-malicious so that you can get a degree t polynomial. And it relies on polynomial interpolation. It encodes the secret. All of that part is there. This Shamir guy is the same guy who is a part of the RSA algorithm. So the S there is the Shamir guy only. So he did a lot of interesting work in this field. So what are the advantages? Looks like life is good, right? You were able to have these participants talk to each other without knowing the data. So it promotes privacy and utility, and it only reveals the final result. And it is less resource intensive compared to some of the techniques that we've seen. But there are disadvantages. Think about the case where you have thousands of nodes or millions of nodes. Communication is an overhead. So if all the participants have to talk to each other, I just showed you 3 nodes that you had to average out or sum the information. But there is a communication overhead, and that will be very, very difficult to circumvent in this case. And it is vulnerable to attack from colluding parties. So the assumption is that t plus 1 folks or nodes give the right response, but that may not always be true. So this is an interesting problem, and there are startups actually that are trying to, some of them are based out of Europe, that are trying to solve this to remove the communication overhead part of it so that it's more scalable. Now coming to the last technique, homomorphic encryption. This is the holy grail. The day we have this thing working fine, probably we will be able to give you recommendations without knowing what you've watched in the past. So what homomorphic encryption is it makes your data unreadable, and it can still do math on it. Let's say that you have an entry in the cloud today. You created some data entry in the cloud, and you want to add some information to that data entry. Typically what you do is, and I'll talk about S3, what you do is either you use client-side or server-side encryption. So you encrypt the data, you send the data, and it's stored in the cloud. Let's say you want to add something to it. The way you do it is, if you have used client side encryption and if your software is running on premise, you bring the encrypted data back, you decrypt it, you add the number, you re-encrypt it, and you send it back. If you have code that runs on the cloud itself, you still have to do the same process, but the decryption happens on the cloud. So there is a window of vulnerability where the data is decrypted to edit the data. But what if I told you, instead of that, you can edit the encrypted data in the same way and the result will still be the same? That is what homomorphic encryption claims. What it claims is that it's a technique of encryption where you can run algorithms on encrypted data itself. So if I were to add two encrypted numbers, 10 and 20, the addition function would be such that the result is the encrypted form of 30. So you do not have to decrypt each one of them, add them, and then re-encrypt them. And I have an example to show that as well. So operations on encrypted data and then decrypting the result is the same as the operations without encryption. And there are several types of homomorphic encryptions, and this gets into the technicalities. That's why it's very complicated. I also had to break a lot of my head to understand what exactly do these types even mean. And I'm trying to oversimplify it here, but for those who are very curious, please go online and read about these. It'll take a long time to finish it. So just a caveat. So there is partial homomorphic encryption, and I'll try to do my best to explain it in simple ways. Um, because some of it is like it, people that have explained it also don't like have not done a good job as well of explaining it. But what partial homomorphic encryption allows you to run select functions unlimited number of times. And this means that one operation can be performed in an unlimited number of times on the ciphertext. And it is the foundation for RSA encryption, which is commonly used in establishing secure communications through SSL and TLS. The next one is a somewhat homomorphic encryption. And it allows limited operations. For example, in homomorphic encryption, there are only two operations that we need to implement. One is addition and the other one is multiplication. The claim is that if you can solve for only these two operations, most of the algorithms will work. It's similar to if you remember the NAND gates and the NOR gates. You can represent any sort of electrical circuit by just using NAND or NOR. In the same way, these are the two operations that we want to build for. And somewhat homomorphic only allows a set number of times. And fully homomorphic encryption, it is the holy grail because it allows us to perform arbitrary operations on any number of times. So what it does is the following relationships hold. If you encrypt two numbers, the encrypted number A and B, and if you sum them up, it will be similar to encrypt A plus B. And similarly for multiplication. There has been it is used extensively nowadays in private ML, and one of the most well-known works in this space is CryptoNets, which combines the homomorphic encryptions and neural network to allow for outsourced machine learning. And in this, I mean, it's done at a very small scale just because, and I'll show you with an example why I'm telling you this. It is commercially not very viable today. It is very difficult to handle noise in this case. So when you are, the problem is that every time you perform a homomorphic operation, we add additional noise to the ciphertext. And if at some point the noise gets very big, then you will not be able to decrypt the ciphertext successfully. So if you are thinking about addition operation, addition will not add the noise to a large degree. Like the noise doesn't grow too badly. And the problem lies with multiplication, because if you're multiplying two numbers and performing a multiplication operation, then the noise effect is multiplicative. So every now and then you have to reset the noise back to 0. This is an example that I was able to run locally. And there is a reason why I tried the addition operation only, because the multiplication operation, it was just impossible to find the right library even today to run this thing. Uh, in this case, I have two numbers, 10 and 20. And without homomorphic encryption, I just added these numbers. And I calculated how much time it took to add the numbers. But with homomorphic encryption, what I did was I used Payer's key pair to give me public and private keys, and I used that to encrypt the first number and the second number. So I got two encrypted numbers. Here, I actually summed them up. I summed up the encrypted numbers, and here I am decrypting using the private key the sum and calculating the time it took. Intuitively, it should not, like, if you're doing the same operation. But interestingly, if you see here, for non-homomorphic, it took 500 nanoseconds. For homomorphic, it was 1.6 million times slower to add these numbers. And therein lies the challenge with homomorphic encryption. It is extremely slow. And this is the case of addition. Multiplication is even slower. So why don't we use it? Like I said, impractically slow. When IBM released its C++ library in 2016, an engineer said it ran trillion times slower. You can expect an engineer to use that language. But now it's down to 75 times, so it's making progress. When I tried it with this library, it was like 1.5 million times slower. So I did not pick the right library, I guess. Microsoft has simple encrypted arithmetic library called SEAL. And this just shows what I just described about homomorphic encryption. So what does the future hold now that I've talked about these four techniques? Several techniques rely on strong computational resources. And the homomorphic encryption is very aspirational, but it needs a lot of research and user experience development. There are many libraries out there, but there is no clear user interface, and there is no benchmarking for homomorphic encryption as well. The interoperability of these libraries is also very questionable. Um, SMPC, the Secure Multiparty Computation, has a lot of message exchange. So there is some ongoing research on can we remove consensus. Nilian is a company that is trying to look into this. And what it does is it tries to solve the problem by having a different type of secret sharing algorithm than the one that I explained. Ideally, what you would want is fully homomorphic encryption. But until we get there, we want to be able to use secure multi-party computation without message passing. And we want differential privacy providing us the framework to quantify the risks. Um, that's my time and talk. Feel free to connect with me on LinkedIn, and I can take questions now. Thank you.